Okay. So, oh, and I'll make a note here that we're doing 6.5 today, and that's going to be our last section. There is a 6.6, which you can read if you want to. It's really just kind of being able to read these problems and figuring out what kind of problem it is. But we'll tackle that in this section as well. So we're not doing that last section, but this is our last section of financial math. Sad face. Everyone loves financial math. Or not, maybe not. So far, what's that? Oh, I see it. The guy out in the hallway. So far, right, we've solved for the accumulated value of an amortization, or sorry, not an amortization, an annuity, and the present value, payment amount, right? And so the last thing that we kind of need to tackle is the outstanding balance on a loan. And so usually what happens, so one of the most common problems is when we have to find the balance owed at a given time during the life of a loan. And so if a person buys a house and amortizes the loan, meaning paying it off over 30 years, but then decides to sell the house a few years later, right? That happens. Then at the time of the sale, he's obligated to pay off his lender, right? He borrowed the full amount and he committed to paying off this full amount. So of course, then what they need to do is figure out, well, how much do you owe today? And then usually from the sale of the house, they take that money and they pay off that loan and they pay that amount off. Okay? And so to find the outstanding balance of a loan, what we need to do is we need to find the present value, P, of all the future payments that haven't been paid yet. What that's going to look like is maybe today we bought a house. Here's a house. Looks kind of like a mushroom, I guess. Whatever. There's a house that we bought, and we've committed to paying this off for 30 years. And so 25, 30 years is pretty typical for mortgages. And so maybe we're paying monthly, so 1 month, 2 months, and 30 years has how many months? 30 times 12 is 360 months. So you're making 360 payments, and so on and so forth. So you've committed to paying 360 payments. Let's say for simplicity that you're paying maybe $2,000 per month. For 30 years. So then the scenario is this. What if you decide maybe at the 10-year mark to sell your house? Seems reasonable, right? You've been there for 10 years and now you're going to sell it and you're going to buy something better, bigger, smaller, cuter. I don't know. Right? And so then what happens? Well, up until this point, you've made these payments, right? You committed to making these payments, and so they've been paid, right? It's these payments here that we still need to figure out, okay, well, what's the equivalent value of these payments today? Right? Very similar to what we did last day. right? And so these guys are going to map back to some present value, right? Remember we talked about, okay, you won the lottery and you get $1,000 a month or whatever it was for 20 years, or you take what cash amount, right? So then we figured out the present value of $1,000 a month for 20 years, right? And so we're doing that same thing, okay? But the only change really is this time span now, right? This time, right? This length of time that we have to figure out and work with has to be the amount remaining, right? The payments that you haven't paid yet, okay? And so here I'm going to highlight T represents the time that still remains on the loan, okay? And so T would be this length of time, right? Whereas before it's just been the 30 years, right? And so now, depending on when we sell this, right, that T has to be adjusted because it has to be the amount of time that's left, right? The time that's passed, that's gone, that's done, okay? So P, so where P is the amount or the outstanding balance that needs to be paid off. So if we ignore kind of these payments that have already been made, then we're back to exactly the scenario that we were working with last day, right? And so the only change really is to adjust this T, right? It has to be the amount of time that you owe payments for still, okay? Which means that N times T is the total number of future payments, right? But in our calculations, those will just happen anyways, right? So as long as you remember that T has to be the amount of time remaining on the loan, then you're good. Huh? So let's see here. I'll bring this up here. We're going to use the same formula that we used last day, right, on Monday, which was this formula here, right? And it's on your formula sheet. And if you didn't get a formula sheet yet, they're up here. And of course, if you haven't grabbed your test, but I think everyone here has, then you should grab your test after class. So if we have a payment of M dollars made N times a year at an interest rate R, then the outstanding value of the loan when there are T years still remaining, that's important, is given by this formula. Notice that it's the exact same as the one we were working with last day. So all we're really doing is adjusting the T. So sometimes you'll have to, or often you'll have to calculate T, which is the original term of the loan minus the time that's already passed, right, since the start date of the loan, which I think you can see quite clearly, right? If you buy a house today and then you sell it in 10 years from now, then you need to pay off 20 years worth of payments, right, in a lump sum. Okay. Let's have a look at an example. Oops, my page is all weird. Mr. Jackson bought his house in 1995 and financed the loan for 30 years at an interest rate of 7.8%. his monthly payment was $1,260. Then in 2015, Mr. Jackson decides to pay off the loan, find the balance of the loan that he still owes, right? Maybe he just came into some money and he wants to pay off his mortgage, or he sold it, we don't know. But it doesn't matter. So what we want to do is map out the entire length of the loan, right? The 30 years first. So here in 1995, he bought his house. And maybe I'll put this up top here. For 30 years, 1995. Oof. Is that 20? Is that this year? It is, isn't it? Like, yikes. I remember 1995, so that's kind of disturbing, but all right. Went to Disneyland that year. I know. My first and only time going to Disneyland. 1995, big year for mini Emily. 2025 is when he was planning on paying off his mortgage, but now we've got 2015. Let's put it here. It doesn't actually matter if you kind of space them out, how you space them out, because usually we just do the first couple of payments and the last couple of payments anyways. But we'll put 2015 there. And let's see here. He's making monthly payments. So 1 month in, 2 months in. He's making monthly payments of $1,260. Oops, $1,260. Um, 30 years times 12 months is still 360 months. I should probably remember that. Total 360, yeah.
Do we have to draw the timeline on the test?
You do not have to draw the timeline, but it might help. If you don't like drawing the timeline, it's okay. It is a nice way for you to communicate to me how you've understood the question, right? And so it kind of helps preserve marks, which I know is important, right? And so if you show me, hey, this is what I think I need to solve here, right? Then I can kind of follow that more easily, right? But no, you don't have to put one on there. I encourage you to, but you don't have to. So 2015 is after 1995, is 20 years later. So he's made 20 years of payments, and of course, he's got 10 years of payments owing. I'll say owing here. Which means that, okay, still, if I pick up, and I'm going to start at the 1 month mark again here, because now I'm going to pretend that these are just a new set of payments and I want to find the present value of them. 1 month, 2 months, all the way to, and I'll bump this up. In 10 years, there's 120 months. 1260, 1260, 1260. I guess 1260 here too. We want to solve for P, right? P is the amount, or is the balance of the loan he still owes. Sometimes what we do is we put T equals 10 years on that arrow, just to indicate, or just to remind yourself that you want the length of that arrow. Okay. What are we given? We're given the rate, which is 0.078. He's making monthly payments, which means N must be 12. And M, which is the payment amount, is 1260. And T is 10 years. And I'll highlight that one because it's different from what we've seen before. Maybe they can smoosh out like that. Smoosh. Okay. If you're solving for P with regular payments, right, then we have to use this big formula, which is on your formula sheet, but I'll just grab it from here. Oh. So I want to solve for P. And it looks like I have all of these other components, so we're going to plug them in. I should write out the formula again, but okay, fine. 1 plus r over n to the nt is m times 1 plus r over n to the nt minus 1 divided by r over n. 1 plus 0.078 divided by 12 to the power of 12 times 10 is 1260 times 1 plus 0.078 divided by 12 time to the power of 12 times 10 minus 1. Oof, 0.078 divided by 12. Let's see if 0.078 is anything, divided by 12 is anything nice. I doubt it. Oh, not bad. That's nice. Oh, I have P equals. That's wrong. There. Yeah. I have P times 1. I'm just going to add the 1.0065 to the power of 120 is 1260 times 1.0065 to the power of 120, then minus 1 divided by 0.0065. Let me move these other examples down here. Hmm. 1.0065 to the power of 120. You should get P times 2.175973024, which I'm going to store in A for later. And then I have 1260. Then I have the same number minus 1. Huh? And so because it's on my screen, I'm gonna just take -1 and simplify that. You can do as many steps as you'd like or show as many steps as you would like, but I'll do 1.175973024. And I'm gonna, just in case, store that in B, just in case I lose it. And divide it by 0.0065. Multiplying and dividing, doesn't matter which order you do it in. I prefer to take this number, which is still on my screen, and so that's why I like to use that one. Multiply by the 1260, then divide by the 0.0065. Okay? But you'll find that the order actually doesn't matter as long as you're only multiplying and dividing. Okay? And so I'll do times 1260. So I get 1481.72601 divided by 0.0065. I get 227957.8477. And P times whatever is stored in A. Which means P must be 227957.8477, which is still on my screen. So then I'm going to divide by whatever is stored in A. Divided by, recall A. I get P of 104,761.339. Bless you. Because this is money, I want to see the full, all the decimals, and then I want to see that you've rounded it properly to 2 decimal places. And so you'd have to pay 104,761 and 34 pennies in 2015. I will say that up until here, this is optional work shown. So you don't need to show all those, but what does that also mean? It means you have to show those first 2 rows, so I need to see that you know which empty formula to use. I need to see that you've plugged in the appropriate values, right? And then it doesn't matter because some people are just really quick at the calculator, so that's fine. But then I need to see the unrounded value followed by the rounded value. So of course, as much as you want to show me, cool, but those are the only things that I'm looking for. So must show this work. And must show this work. Nice. Good. Do you think you could figure out how much he bought his house for in 1995?
Probably a lot less than now, though.
Probably. What would that be? That would be the.
Yeah.
the present value of all these payments, right? All the 30 years of payments. So if you did the same thing, but for P back here in 1995, then that's how much you paid.
Which would then be T was 30. Right?
Exactly. Yeah. So that would be the only change. Kind of neat. Because we only have the monthly payment, which I feel like is quite high, but at 7.8%, it'll be pretty high, I guess. Sorry, high for 1995, not high for now. Now, that would be great. So nice. Yeah. I think this one is so cute because then Aisha graduates in the next question. But suppose a baby, Aisha, is born and her grandparents invest $8,000 in a college fund. How nice. The money remains invested for 18 years until Aisha enters college and then is withdrawn in equal semi-annual payments over the 4 years that Aisha expects to attend college. Should probably make that 5. The college investment fund earns 5% interest compounded semi-annually. How much money can Aisha withdraw from the account every 6 months while she is in college? So this is what I would call a two-phase problem, right? We have money that's just deposited and then it's going to sit there for 18 years. Then what's going to happen is that accumulated amount or that future value, that's going to fund the withdrawals for the next 4 years, right? And so this is where it starts getting kind of hard if you don't draw it out in some way, right? And so that's why I introduced the timelines earlier. But what would this look like? So we've got this timeline, long timeline, and so Aisha is born there. Probably not today, but Aisha is born there, and then 18 years later, there's a change to this money. All right. So what happened? Her grandparents invested $8,000, and it's gonna sit there and grow to some accumulated amount for 18 years. Then what's going to happen? Then she's going to withdraw equal semi-annual payments over the 4 years that Aisha expects to attend college. So now what's going to happen is this length of time is going to be 4 years. With semi-annual payments, right? And so that means that there's going to be 8 payments, right? And I'm going to, instead of doing 18 plus 4, which is 22 years, I'm actually just going to call this 4 years because that's just the length of the payments, right? But what happens is I'll use semi-annual. So let S be semi-annual. Right, 1S, which is the first 6 months, right? 2S, blah, 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 blah. 7S, 8S. So 8 semi-annual payments, yeah.
And are these gonna be?
N is 2. So here, therefore N is 2, if that's what you mean. Now, these amounts, and we don't know what they are. In fact, we need to solve for what they are, right? And so here, we want to find M. Bless you. How are we going to link these up? Well, and here's the tricksy part, but once you've seen it a couple of times, then you're gonna start to think, oh, I know how to do this. These guys, those payments have some present value, right? P. So what's gonna happen is this accumulated amount, right, from the 8,000, it sat there for 18 years and it earned interest and it just kind of compounded semi-annually. And so then it earned interest. Then I have this accumulated amount, which is then going to turn into the present value or the principal amount to support these payments going out, right? And so here's the key, is that we first need to solve for A and then use that A as the P for the payments. And so here, I'll just add a page here instead. We need to solve for A, then use that amount as the principal amount for the unknown payments. Let's figure out. I wish I had more room, but anyways, what are we given? We're given $8,000 is invested, right? And so, but that part is relatively straightforward. And then we've got semi-annual payments, which means that our N must be 2. For 4 years, which means that T must be 4 years. And the fund earns 5% interest compounded semi-annually. And so R is 0.05. Now, if it doesn't help you, that's okay. But what I'm going to do is I'm going to talk about kind of this chunk of calculations as phase 1 and this chunk of calculations as phase 2. Because we need to solve phase 1 before we can solve phase 2. So phase 1, we're given that P is 8,000 and we want to find A. Notice that there are no regular payments in phase 1. Right? And so then, where are you going to look on your formula sheet? Then we're here. We want the future value. We have some P, and I want to find A for just a compound interest problem. So I'm gonna copy this and bring it in so that I have it. So A is P times 1 plus R over N to the N times T. A is going to be 8,000 times 1 plus 0.05 divided by, 2 times 2 or to the power of 2 times 4. Not 4. Oops. I need to add that T is 18 years in this case. And I'll swap these. Oh, and this is 18. Because it's going to sit there for 18 years. So let's see here, 0.05 divided by 2. It's looking good. I get A is 8,000 times 1 plus 0.025 to the power of 2 times 18 is 36. So A is 8,000 times 1.025, oops, to the power of 36. 1.025 to the power of 36. As long as I keep it on my screen, you don't have to store it, but you can if you want to. 2.432535316. Multiply that by $8,000 and you get 19460.2825. Rounding, because this is money, 19,460.28. So what this means is that this 8,000 over 18 years grew to $19,460.28. So now that's the principal amount that you have that will sustain these unknown payments that we're trying to solve for. So now, moving on to phase 2. Oh, and I should move this down actually, because this is for phase 2. We're given that T is 4 years for phase 2. And from phase 1, P must be 19,460.28. And so here, right, this A turns into the P, right? Because it's really just the position in the money chain that determines if it's an A or a P, right? So if it's at the start, it's a P, and if it's at the end, it's an A. Okay, so now we want to find M. We have our go-to formula, so as soon as anything involves M, right, a payment amount, then there's really only one choice on your, or I guess 2 choices on your formula sheet, but because I don't want to find A, right, I don't want to be saving money and then figuring out how much I have at the end, right? I want to solve for, or I have P and I want to solve for M, which means that this is my only option. Huh? So I'll just write it out here. P times 1 plus R over N to the N times T is equal to M times 1 plus R over N to the N times T minus 1 divided by R over N. Now P, this is really the only tricky part, right? Besides combining the two problems, that's tricky, right? But also taking this A and knowing to turn it into a P, that's kind of tricky as well. But once you've seen it, right, then you say, oh, okay, I know how to do that. Right? And so now I have a P, and you want to make sure that you use the properly rounded value, right? Because the bank only gives you 2 decimal places. So we get 19,460 and 28 cents. But you want to use all the decimal places because it's your money. 1 plus, and I think we have the same interest rate, 5% for both of these phases. We will see a problem where they're different, right? So then you want to be really, really careful. And so, but it's 5% still. And so 0.05 semi-annually divided by 2, and then N is 2 and T is 4 now. M times 1 plus 0.05 divided by 2 to the power of 2 times 4 minus 1 divided by 0.05 divided by 2. Okay. 0.05 divided by 2, I'll do plus 1. 19,460.28 is 1.025 to the power of 8, which is M times 1.025 to the power of 8 minus 1 divided by 0.025. 1.025 to the power of 8. And I'm just going to multiply by 19,460.28 right away on this side here. 23710.46154. I am going to store this because I'm going to need it later. Store it in A. And then I have M 1.025 to the power of 8 minus 1 puts me at 0.218402897.5 divided by 0.025. I'll add a page here. Since these are all multiplying and dividing, right, those are on the same level, and so you're allowed to take this 0.2184 blah 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 divided by 0.025 and make this one number. So divided by 0.025. Actually, I'll just write what's stored in A because I'm lazy. M times 8.7361159. Solving for M, I need to divide both sides by this 8.7 blah blah blah. And so I get M is 8.7361159 divided by what's stored in A. Now I keep the 8.736 on my screen, on my calculator, divided by recall A. What happened? It's looking really bad for Aisha. Something happened here. Because I got 0.00036 something. Oh, I know what I did. I swapped them around. It was not looking good for Aisha there for a sec here. Let me just, there. Phew. Okay. Now, recall A divided by that guy. That looks better. A lot better for Aisha, $2,714, 0.073601. So in money, 2,714.07. Therefore, Aisha will get $2,714.07 every 6 months for the 4 years she's in school. It's nice of her grandparents. Wouldn't that be nice? They just, when she was born, they put in $8,000 and it just sat there. So that's pretty good. Yeah, it's really, it's hard to find 5%. Yeah. Curious to know, I think sometimes you can get like 2%, I want to say, but usually it's lower.
4% for the next steps.
Pretty good.
Not as good as 5.
You could rework it and see what she would get with 4%. 5 is really good. Okay, nice. How about a similar problem, just slightly different? So Aisha graduates college and starts a job. She saves $1,000 each quarter, depositing it into a retirement savings account. So now she's working and she's saving $1,000 every quarter and she's putting it into an RRSP. Suppose that Aisha saves for 30 years and then retires. At retirement, she wants to withdraw money as an annuity that pays a constant amount every month for 25 years. Uh-oh, this is adding up to be a lot of work, isn't it? All right, because she's saving money, she's got these regular payments, she's saving money, and then she's going to use that saved money to withdraw payments for 25 years. During the savings phase, the retirement account earns 6% interest compounded quarterly, which is good because it matches the payment frequency. And during the annuity payout phase, which we'll call phase 2, the retirement account earns 4.8% interest compounded monthly. Monthly is good because she wants monthly payments. And calculate Aisha's monthly retirement annuity payout. And so I'm gonna call the savings phase, I'm gonna call it phase 1. And then the annuity payout phase, I'll call it phase 2. Oops. I just find it's helpful to think of them in terms of, okay, phase one, phase two, right? So now, even though they're not quite the same distance, what I'm gonna do is just make a nice long timeline and split it in half. So that I can see what's going on here. So here she graduates. Graduation, woohoo. And for 30 years, let's put that here. We hit retirement. Also exciting. A lot of time passed in between there though. And then not sure what I'm gonna put here, but this is 25 years after retirement. I'm not gonna say that she dies here because that's probably not true, but 25 years after retirement. So we'll call this phase one, and we'll call this phase two. So she's gonna make quarterly payments. So first quarter, second quarter, and for 30 years, there are, 30 times 4, there are 120 quarters. So 119 quarters, And she's gonna put away $1,000 each quarter. In phase two, she wants to withdraw money at a constant amount every month for 25 years. And so in phase two, we've got the 1 month, 2 months, and for 25 years, there are 300 months that she's gonna get payments for. Now, we don't know these payment amounts, that's our job. We wanna find these payment amounts, but I am just going to write M to show that that's what I'm gonna solve for. The direction of the money, or kind of how the money is leaving her and coming back, does make some difference, right? Because here she's saving these $1,000 per month, right? And so she starts with nothing, right? The present value, she graduates, she's got nothing. The present value is 0, right? And so we kind of ignore that. But what happens is for these 30 years, that's going to build up to some accumulated value, right? Some A. Then we use that same trick that we just saw, where we say, okay, now I'm going to change what's happening with my money, and instead of putting money in and adding to it, now I'm going to take money out, right, in equal amounts. And so now this is going to be P for those payments. Right. What we're given for phase one. And then I'll do the same thing for phase two over here, and maybe I'll put them on the same line. We're given that she's going to save M is 1,000 every quarter, so N is 4 for the first part. And T is 30. And here's the tricksy part where you need to really be sure that you have your values in the right spots, right? Because during the savings phase, which we're calling phase one, the retirement account earns 6% interest compounded quarterly, which means that R is 0.06. And compounded quarterly is good because that matches the payment frequency, which is 4. And we want to find A. In phase two, we're given P from phase one, sort of, right? Or we will have it. So that's where I'm going to start. And we have T is 25 years. I should say years. And now she wants monthly payments for 25 years, which means N in this case is going to change to 12, right? And so, and then just make sure that the interest rate is also compounded monthly, which it is. So N must be 12. And the rate is 0.048. And we want to find M. Okay. So I am going to highlight the different rates, right? And the different ends. I mean, everything is different. And so, but I do want to highlight that they're different rates, especially. Okay. Let's start phase one. We have to find phase one first. I have an M and I want to find A. If I want to find A with a regular payment amount, then I know that I want to use this formula here. Right? It's been a while since we used this little guy, right? And so let's bring it, I'll just copy it into our notes here. And I'll write it out just for completeness. M times 1 plus R over N to the NT minus 1 divided by R over N. That looks familiar, right? It's just the right-hand side of what we're usually working with, but just a little bit more compact. I know M, oops, is 1,000. I'm going to try to keep it times 1 plus 0.06 divided by 4 to the power of 4 times 30 minus 1 divided by 0.06 divided by 4. Let's see, is 0.06 divided by 4 anything nice? It is. That's exciting. It doesn't really make a difference, but it's always just kind of nice when it's a nice number.
Don't we wanna find? No, and with.
Yeah, so what's gonna happen is we wanna figure out, okay, all these add up to what, A? But then this A amount is going to turn into P for the next phase. So that's the sticking point. But first we have to find A, and then it turns into P, which is confusing. And then we can solve for it. So A is going to be 1000 times 1.015 to the power of 4 times 30 is 120 minus 1 divided by 0.05. 1.015 to the power of 120 A is 1000 times, I'm just gonna do the -1 right away, because I'm lazy. 4.969322872 divided by 0.015 times 1000 divided by 0.015. 33128.1915. Pretty good. Good job, Aisha. Oops. $331,288.19 is what she'll have saved after 30 years. Oh. I can just bump these guys down. So now that's how much she's going to be withdrawing from, right? Monthly withdrawals for 25 years is what she's planned. So how much will she be able to withdraw each month for 25 years? That's phase 2. So now I'm just gonna copy what we were given so I don't have to scroll around so much. And P is going to be this $331,288.19 from phase 1. Right, but now it's a P. Now, if I have a P and I have an M, or I want to find M, then I need to use that biggest formula, right? And so I have P times 1 plus R over N to the NT is M times 1 plus R over N to the NT minus 1 divided by R over N. Really, too bad if I had memorized that wrong. Too far gone. I should probably check. Although I feel pretty good. We've done it so many times. Once it's in, right? I'll just sneak it up here. It's the same, but. Good. Okay, so now, same scenario that we've seen before, right? I have the P, and as long as you remember to change your R and your N and your T, so basically everything, then you can solve for M. So 331288.19 times 1 plus 0.048 divided by 12 to the power of 12 times 25 is equal to m, which I want to find, times 1 plus 0.048 divided by 12 to the power of 12 times 25 minus 1 divided by 0.048 divided by 12 is 0.048 divided by 12. Phew! Gonna just go ahead and do +1 because it makes it nicer looking on my calculator. 33128819 times 1.004. 12 times 25, oops, 12 times 25 is 300. I can remember the formula, but I can't remember what 12 times 25 is. Calculated it so many times. 300. (1.004) to the power of 300 minus 1, oops, divided by 0.004. Okay. I'm going to simplify the whole left-hand side first. And so I have 1.004 to the power of 300 times, and then times 331,288.19. And I get 1097285.895. It's tempting to round that to 2 decimal places, but you want to keep all your decimal places because we're not done yet. Yeah.
So I did phase one myself.
Okay.
It was mostly correct except for the decimals that turned out.
This one at the very, very end.
Oh, we never.
You're okay?
Yeah.
Nice. And good work. M times, and then I'm gonna do 1.004 to the power of 300, then minus 1, then divided by 0.004. M times 578.044837. Oops, and I'm just remembering now I forgot to store, but I'm gonna store this in, I'll call it B. I forgot to store this in A, but I'll go back and redo it. Store it in B. And I have to redo it. Now, M is going to be what's stored in A divided by what's stored in B. Recall A divided by recall B. One 898.271,264. As money, 1,898 and 27 pennies. And I'm gonna just check the time. He makes me so nervous because it's so quiet over there. Lots of time. What does that mean? means that she went from saving $1,000 every quarter for 30 years, right? To getting $1,898.27 per month for 25 years. That's pretty good. Nice. Any questions about that one? So the last thing that we're going to talk about in financial math is the amortization tables. And so an amortization table or schedule for a loan. Yeah, sorry,
We're not doing 6.5. The example,
I guess I skipped it.
because it's. The Orange Computer Company needs to raise money to expand, issue the 10-year $1,000 bond that pays $30 every 6 months. If the current market interest
Oh,
rate is
I'm skipping bonds, that's why. And, oh, that's it, thank you. That's a good thing, because I wanted to highlight that you can skip some questions, I know. For the homework for this section that we're doing right now. There's a typo in question 12, it should refer to question 11, not 13. And then we're not doing questions 13 through 16, which is on bonds. And so you can do them for fun if you want to, but you don't have to, because we're not gonna do them. Thank you for that reminder, because I totally forgot that I was skipping something. Sneaky. But we are doing the amortization schedules. Well, let me see, let me just make sure these problems here. Oh, yeah. So there you've got your yeah, it's just bonds that we're not doing. You can try them on your own, but I decided no. Okay. So an amortization schedule is going to be a table that lists all the payments on a loan. Okay? And what's going to happen is it splits them into the amount of interest that you have to pay, and the portion that goes towards paying off the principal amount, the original that you borrowed. And so even though we make the same payment every month, at the very beginning of the loan, most of that is going towards paying off the interest, right? Because we've committed to paying interest, and the bank says, hey, first things first, we're gonna take our interest, and then we'll use the rest to pay off your loan, right? And so it's not all paying off the loan. They take their interest amount first, and then whatever is left over pays off the loan. But as the balance decreases, then the amount of interest that you have to pay is lower, right? And so what happens over time is the amount of interest that you pay is going to go down, and for each payment, and the amount that you're paying off of the loan is going to go up. And so an amortization schedule or table shows that. So what I'm gonna do is show you by example, but a general table, or maybe let's do this instead. Sorry, I had a change of heart. I'll save this and paste it down here. And I'll just introduce the actual table or the bare bones of the table. Okay. So the typical headers of an amortization schedule is the payment number, right, which is going to go from 1, 2, 3, all the way down to n times t. Right? However long you've committed to paying for at what payment frequency, right? And this should be n times t. Looks spaced out. Oh. The payment amount is going to be your m. Now that payment amount is going to be the same always, right? For every single payment. And so we have M, boop, 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 M. Sometimes we have to adjust that final payment because there's not very much owing, but let's assume that it stays M. Well, the interest that you owe is going to be for each payment. Okay? And so here, what's going to happen is this is going to be, oh, sorry, I equals PRT, okay? Where the T is for one payment. For one payment. So effectively what happens is, sorry, it's going to be the rate divided by the payment frequency. Okay. Now P is going to be the loan amount to start. I'm putting it up above the balance because then what's going to happen is this balance is going to turn into the new P. And so here we're going to have a P1 after, so that's going to be the balance after payment 1. Okay. And notice I'm skipping a column for now, but that's on purpose because let's just focus on this I. The amount of interest is now going to be P1 times R times T. So it's going to take that previous balance and calculate the amount of interest. And so, and then you're going to get P2. Now, how do you find that balance? Well, you're making a payment of M, right? And the bank says, hey, first, we're not paying off your loan. We need I, right? We need this I first. So they take that. So then whatever is left over though is removed from your M, right? And so here this becomes M minus I. Now what we can do if you want is you can use little I1, I2s, I1, because we're going to have different I's for all of these as well as P's, right? Because each line is going to be different. So then what's your P? Your balance owing is going to be the original P minus however much you're paying off. Okay? And so let's give myself just a smidge more room here. P1 is going to be P minus M minus I1. But notice that that's just whatever value you found here. Okay? And for P2, it's going to be the previous balance, P1 minus M minus I2. because this is going to be m minus I2, and so on and so forth. Hmm? Pop, 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 pop. Until you're paid up, which you will be, and then the balance owing will be 0. Huh? Or sometimes it's like $5 or something. They say, hey, give us our $5. You say, no, I paid this much. They say, you have to give us the $5. Right. So sometimes due to rounding, it's not 0, but it'll be close. So what does one of these columns actually look like then? Huh? Now, because I use this formula, because we're familiar with it, we've seen it before, right? Every month, let's say, is going to act like simple interest, right? Or what we can say instead is we can say, okay, well, what if I just always take r times t and I use that as a lowercase I? Maybe I've gone too far. Forget it. We can just use the formula that we have. Sometimes we convert it to a lowercase I, but for each period. But we've got what we need. Sorry. I don't want to confuse you. Now we're ready for an example. An amount of $500 is borrowed for 6 months at a rate of 12%. Make an amortization schedule showing the monthly payment, the monthly interest on the outstanding balance, and the portion of the payment contributing toward reducing the debt and the outstanding balance. And so we're going to have this table here that we're going to fill in. Before we can do that, we need, so we're given P is 500, right? The initial amount that's borrowed. T is 6 months, so 6/12 of a year. Or half a year if you want. At a rate of 12%, so the rate is 0.12. And what else? N is monthly, oops, N. So it's 12. And we want to find, or we need to find M, right? We have the payment numbers. If we're making monthly payments for 6 months, then we can fill that in, right? 1, 2, 3, 4. Maybe it might be nice to start with a 0 line here. It's up to you. I did the 0, kind of a 0 line up here. 0, there's no payment, no interest, no debt. But it does the same thing. I need to find the payment amount, M, right? And so here, I need to solve that. And then I'll be able to solve for the interest and the debt payment and the balance. Okay. So I'm going to bump this down a little bit. How are we going to solve for M? I have a P. I need an M. There's only one formula that will do that for us, right? And that's that big formula that we've almost probably memorized already. P times 1 plus R over N to the N times T is M times 1 plus R over N to the N times T minus 1 divided by R over N. Let's see here. P is $500. 1 plus 0.12 divided by 12. Well, that's nice. 12 times 0.5. Right, 6 over 12 is 0.5 years. Bless you. M times 1 plus 0.12 over 12. 12 times 0.5 minus 1 divided by 0.12 over 12. Point 0.12 over 12 is going to be nice, which we're grateful for. So I'm going to do plus 1. (1.01 to the power of 6). M times 1.01 to the power of 6 minus 1 divided by 0.01. (1.01 to the power of 6). Times 500. Just simplify this left-hand side first. 530.7600753. Now I'm going to store this before I forget again in A. M times 1.01 to the power of 6, then minus 1 divided by 0.01. I get M times 6.15201506, which for good measure, I'll store it in B. M then is going to be what's stored in A divided by what's stored in B. I did something weird. Recall A divided by recall. That explains why it was so quiet over there. Sounds like they had a test in there. 0.274183336. As a payment, we get $86.27. Nice. To calculate the interest, we find that I is going to be PRT. The P is going to change, right? And we're going to allow it to change. So I'm just going to hold it as P. But the R times T is going to be the same always, right? Because the rate's not changing and the amount of time for one payment has to be the same, right? And so I is going to be P times, what was it, 0.12 and monthly payments. 0.12 times 1 over 12. Okay? And that's because, and that's basically R over N, right? But I'll explain the 1/12. I think the R is okay, but it's the 1/12 that might be confusing, right? And that's because each payment is just a time point of 1 month, right? And so each payment has T equal to 1/12 or 1 month. Oops. So you want to break it down for each payment. Okay. So maybe let's do this. We'll say the payment, I'll start with a 0. I probably should have done that in the first table, got carried away. But then the first month, second month, third month, fourth month, fifth month, sixth month. Because it'll be the entirety of the loan. Now we already found the payment amount. Now that payment amount is going to be the same, right? And so it's going to be what we found, the 86.27. There's no payment here. The only reason I have this 0 line is to put the original balance of $500. $500. And then the 86.27, 86.27, 86.27, 86.27, and 86.27. Sometimes we adjust that final payment. We can ignore that. So next up, we need to find the interest, the amount of interest that's owed. The amount of interest is going to be off of the previous balance, right? And so P in this case, so here, this is your I, is going to be P times 0.12 divided by 12 times 0.01. All right, and I'll do point. And that's from up or down, I don't know, bringing it down there. And as long as you remember to do the previous balance, yeah.
So technically the T doesn't really matter, right? Because it's just 1/12.
Yeah, the T is just the time of one payment. So it is still T, but when we break it down by payment, right? So the overall amount of interest would just be 6 months, right? Because we're paying it off over 6 months. But for each individual payment, it's 1 month. Right? So that's the only kind of weird part. But what does that mean? It means that, okay, the previous balance, which is going to be your P, times 0.01. So 500 times 0.01 is 5. So 500 times 0.01 is 5. So the bank says, hold up, you need to pay us $5 first. They don't even say that, they just take it. But it's nicer if they ask. So once they've taken their $5, you've paid $86.25, which means that $86.25 minus 5 is going to pay down your debt, right? And so 86.27 minus 5, just to be proper here, puts us at 86.27 minus 5 is 81.27. And I just need a little bit more room. I'm gonna see if I can maybe scooch it over this way. Yeah, that works. Okay. So now the balance that I owe after my first payment has to be 500 minus the 81.27 that they're paying off my loan with. Okay. So this one is going to be 500 minus 81.27. Which puts me at $418.73. Now I can move on to the next line. Right? Now for this next line, I still have to pay interest. I have to pay 1% interest essentially for this 1 month, right? Because it's 12% over 12 months. And so now I need to multiply this balance by 0.01. Okay? And so I get 418.73 times 0.01. Oops, I should change this to green. Actually, maybe, maybe I should show where it came from. I'll just keep that orange times 0.01. And you want to make sure that you round to 2 decimal places. So you make sure that you get 19, right? It is 1873 pennies, but because the 8 is followed by 5 or higher, then you have to round up. Now we have paid a little bit less towards the interest. That's nice. That's a nice feeling, right? Which means we're going to pay more towards the actual debt. Right? And so, but we're still paying the same amount, 86.27. And so we have 86.27 minus, I could have done a better job color coding this, I guess. 419. I get 82.08. Now from the previous balance, right, 418.73, I can take away 82.08. Okay. And so I get 418.73 minus 82.08. Let's see if I can, 418.73. And 336.065. Tiny. That should be 65. Squint. See it. Instead of showing all the work, I'm just going to write out what the answer would be and just make sure that you get to the same answer. So now, what do you have to do? Now you have to take 336.65 times 0.01, right? And so now we take this times 0.01 and make sure you round to 2 decimal places. So I get 337. Because it's 3.3665, but I'd have to round up to 37 cents. Or should I show it again? Should I show the work again? No. I will make a note here that make sure you round I to 2 decimal places properly. Right? Is it still money? If the bank takes 337 and I've paid 86.27, then how much 86.27 minus 337? Then I'm paying off. It's going slowly, but I'm paying off $82.90 from the 336.65. 336.65 minus 82.90 puts me at 253.75. Now we do it all over again. 253.75 times 0.01. Yeah.
I just wanna let you know that we. 3 minutes.
Oh my gosh. Power mode times 0.01. Thank you. So I should be worried when it gets quiet over there, I guess. 254, 86.27 minus 254. Paying off 83.73, 253.75 minus that. It's only because I want you to see the last line. What it looks like. $1.70. $4.57. Oops. 85.45 times the interest, 0.01, because they'll make sure that you pay your 85 cents in interest. I'm getting there. Which means you would still owe a little bit of money, but not too bad. $0.03. I think you can come up with that. Sorry to keep you so long. If you have any questions, let me know. Otherwise, enjoy your Halloween. That's important. And enjoy your weekend. I'll see you on Monday. Stop this recording.